Hello all, welcome to this course on time series modeling and forecasting using R. Okay. So, this week the focus area that we are talking about broadly speaking is non-linear time series models. So, all the models we have studied so far, so be it autoregressive, moving average or ARMA or rather ARIMA, SARIMA. So, all these were examples of linear structures or linear time series models wherein one can actually encounter a practical application and one can put forward a linear sort of a structure to model that. Okay. But of course, as probably all of you might know that let us say if you bring any practical area of concern where time series modeling and forecasting would be required. So, non-linearity is kind of predominant, right. So, one need not expect every time that the underlying practical data set has to be linear. Okay. So, we require some sort of a shift from a linear structure to capture the non-linearity from the time series process as well. Okay. And the very first session, in fact the last session or rather the first session of this week was focusing more on the introduction part or rather the motivation part as to why should one make that transition from linear time series models to non-linear time series models. And even in the last session we talked about several examples of couple of very important non-linear time series models, let us say threshold models, etc. right. And there if you sort of remember we talked about an idea called as regimes. Okay. So, again just a very short kind of an overview as to what do you mean by regimes first, and then of course, as you see the title of this session is a few more aspects on regimes and a few non-linear models to specify. Okay. But before we start with anything new, again as discussed a short while back, that what exactly does one mean by regimes. So, the word regimes means nothing but states. Okay. So, imagine that you have a practical time series split up into different states or different phases. So, all these states are called as different regimes of the time series, and one very differentiating point is that any two states or any two regimes are not exactly the same. Okay. And all these regimes are kind of divided by threshold variables or rather threshold values or threshold levels. So, as whenever a time series transitions from one state to another or rather one regime to another, you see a dynamic shift. Okay. So, any two regimes or any two states or any two phases need not be exactly equal, and hence one requires a slightly differentiated sort of an approach to model inside each of the regimes. Okay. So, now in today's lecture we will talk more about regimes and a few more non-linear models to start with, and towards the end of this week I am pretty sure that we will discuss a lot of examples, and then again we will sort of link back all the examples to the first initial motivation as to why should one in fact transition from this entire area of linear time series processes to non-linear time series processes. Okay. Alright, so the first slide is modeling regimes. So, again the initial part will discuss a few kinds of regimes, and then in front of you have different kinds of regimes, starting with the very first one which is called as threshold based regimes. So, these are kind of very easy to understand, and then down the line we will see that you may encounter some slightly advanced kind of a regimes which we will discuss very soon, but then threshold based regimes form the base structure, and then some of the advanced regimes are kind of extensions of these threshold based regimes. Okay. So, before we start with anything very deep into technicalities etc., we will define what exactly does one mean by regime. So, regime definition from a mathematical perspective or from a technical perspective. So, let us say that you have a very small illustration, very easy also, and then here we are considering two regimes. So, regime 1 and regime 2, and let us say gamma is the threshold value. So, this gamma that you see here is the threshold value or the threshold level, and y t minus d is the actual time series progression. Okay. So, inside regime 1 what is happening? So, inside regime 1 we will say that the time series yt and obviously all of its past lags are inside regime 1 as always as this yt minus d is less than gamma. Okay. So, wherever this time series value in terms of t minus d, which is nothing but the lagged value of the time series itself, happens to be strictly less than gamma, we will say that the underlying time series has not shifted yet, or in other words the underlying time series is still existing in regime 1. Okay. But then since this gamma is the threshold value, as and when the time series transitions from let us say being less than gamma to more than gamma, we have a regime shift here. So, regime 2 is nothing but all those values of the time series where yt minus d happen to be bigger than gamma. Okay. So, I guess it is not really difficult to understand the idea of threshold based regime. So, again just to summarize, there should be one threshold value which is equivalent to gamma here, and then we will sort of compare all the lagged values of the time series with that threshold value, which is gamma, and whenever all the lagged values happen to be less than the threshold value, we will say that the time series is sort of performing inside regime 1, and as in when the time series transitions from one regime to another, or rather the lagged values become more than gamma, we will say that the regime has shifted. Okay. So, again just to summarize what exactly the notations mean. So, as always y t minus d is nothing but the lagged value of the series or another variable, and gamma in this context is the threshold value. Okay. And these are some of the examples where a threshold based regime can be seen. So, let us say TAR or SETAR sort of models. Okay. By the way, TAR model was kind of discussed very briefly even in the last session. So, the full form is threshold autoregressive structure. Okay. And on top of that, this SETAR model is nothing but an extension of a TAR model. Okay, now coming to the second kind of a regime. So, the second kind of a regime is called as a smooth transition regime. By the way, we have discussed these three classes even in the last session. So, the very last slide of the last session, where if you remember very vaguely that we had listed down all the three kinds of regimes there, right. So, starting with threshold based regimes, then the second one was obviously smooth transition regimes, and then lastly we also discussed probability based regimes, where we talked about Markov switching models and all those. Okay. Now, this is the second one. So, smooth transition regimes, and then under the smooth transition regimes there has to be some transition function. Okay. So, this function g that you see given by capital G, which depends on multiple parameters, we will discuss each and every one in detail, do not worry, but then the predominant parameter are nothing but the threshold value. So, the z t minus d is nothing but the threshold variable, gamma in this case is rather the slope parameter, okay, and then c in this case is rather the threshold value. So, again just to summarize, the z t minus d is nothing but the threshold variable or the lagged values of the time series. This gamma is nothing but the slope parameter, and then the c is nothing but the threshold value. And here you can see that the transition function is not very difficult to understand, it is rather 1 divided by 1 plus e to the power of minus gamma into z t minus d minus c. So, again probably one strong suggestion could be that just pause the video and then sort of subsume the information which is given in the transition function. So, try to understand all the components that go inside the transition function. Okay. Now, again as discussed here, so the transition function majorly depends on two parameters rather. So, gamma and c, where gamma is nothing but the slope parameter similar to any of the regression equations you might have seen, and the c on the other hand is called as the threshold value. So, in this context here, if you focus on this piece of the transition function, then you can basically argue that if you compare this difference between z t minus d and c to let us say 0, so whether the difference is less than 0 or more than 0, we could have a transition. Okay. So, in that case we will say that the c is nothing but the threshold value. And some of the examples in this context or in this spirit are star models. So, we will talk about star models in detail probably in upcoming sessions. Okay. So, we started with one kind of a regime which was threshold based regimes, which is kind of on the easier side to understand. But what would happen if we can include the regimes inside a function sort of a thing? So, this gives rise to a smooth transition regimes there. Okay, and now the next kind or the third kind is called as latent state based regimes. So, what do you mean by that? So, latent state based regimes. So, here the main ingredient has to be some sort of a Markov transition matrix. Alright. So, this capital P structure or this capital P matrix that you see in front of you comprising of 4 cells. So, P11, P12, P21 and P22 is called as nothing but the Markov transition matrix. And again, where each of the inside notations, let us say Pij to be specific, is nothing but the probability of transitioning from regimes I to j. Okay. So, all these individual entries, for example, P12. So, what do you mean by P12? So, again you can pause the video and try to think in your minds as to what would be the definition of P12, or how would we define, let us say, P22 for example, right. So, when it comes to P12, so P12 is nothing but the probability of transitioning from regime 1 to regime 2. So, just to mention very quickly here that if somebody is transitioning from regime 1 to regime 2, then what exactly is the probability of transitioning from regime 1 to regime 2. So, in a way all these 4 entries in this matrix are nothing but some sort of a probability. And one major example in this spirit is nothing but called as a Markov switching model, right. So, in this context so far we have studied 3 different sort of a regimes. So, the threshold based regimes, then latent state based regimes, which is the ingredient of the current slide, where we throw in some probabilities. And just in the last slide we talked about smooth transition matrix or smooth transition regimes, where you require some transition function to sort of decide on the transitioning between one regime to another. Okay, so now the next thing we will talk about very briefly is what exactly are the benefits, or what do we get from doing all this, or rather modeling the regimes and so on and so forth. Okay. So, the very first advantage is improved forecasting. So, what do you mean by that? So, by modeling distinct regimes, these models can in fact improve accuracy, especially for systems with abrupt changes. Now, again, just to sort of give you the same visual example we talked about in the last session. So, let us say if you have a time series which is transitioning like that, and let us say if you have a threshold value which is like that, and the moment the time series sort of crosses the threshold value, you can see that the time series behaves as if it is highly volatile here, okay, which means that this could be a threshold value based regime. So, where this is the threshold value, let us say gamma or something like that. So, as in where the time series crosses that threshold value, you can see very high volatility in the underlying time series. And if you are able to capture this entire system very nicely using some of the regime modeling ideas, then it can sort of lead to some improved forecasting. And why exactly? Because what we will do here is that we will try to model these separately. So, this would be regime 1 in our case, and then this might be regime 2. So, if you are able to propose sort of differentiated models for each of the regimes, and then overall we try to connect them, it can give us improved forecasting rather than putting forward one single model to capture the entire structure. So, hopefully the small point is kind of beneficial, or hopefully all of you understood this, that if you divide the time series based on regimes or different characteristics of practicalities, then it might lead us to improved forecasting down the line. Now, the second advantage could be interpretability. So, what do you mean by that? So, clearly defined regimes provide insight into the underlying system. So, if you divide any time series into different slots or different regimes, then it can actually tell us predominantly what are the characteristics inside each of the regimes. So, clearly defined regimes provide insight into the underlying system as well. And thirdly, flexibility. So, it can capture a wide variety of non-linear behaviors, right. So, let us say again, just to give you an example, let us say if you have a time series, and then let me divide this time series into multiple regimes, and due to the highly volatile nature of the time series, or due to lots and lots of ups and downs overall in the entire time series, let us say hypothetically the time series behaves like this. So, initially it might have a trend, but in the second regime it might be slightly volatile like that, in the third regime it might be stationary, for example, like that, and towards the end again it might show some downward trend. Okay. So, again if somebody wants to put forward an overall sort of a model structure to capture the entire time series in one piece, then it might not be very easy. But the moment you divide the time series into multiple regimes, we can actually capture the individual non-linearities, let us say capturing the trend or volatility in the second regime or stationarity in the third regime, etc., by dividing the entire time series into different states or different regimes. So, again just to summarize, improved forecasting, obviously interpretability, and the third one is flexibility when it comes to regime modeling. But having said that, the regime models are not entirely advantageous always. So, what exactly are the challenges of regime models? Okay. So, what exactly are the disadvantages when it comes to modeling using the regime idea? So, the first one is threshold selection. What do you mean by that? So, determining the appropriate threshold value, let us say gamma, or transition function parameters can be computationally intensive. So, again probably let us say that, again just to give you the same example, let us say if you have a time series divided into multiple regimes, but where exactly should you place all these different threshold values or threshold levels, right. So, that could be a challenge, alright. So, one has to identify exactly as to where the change is sort of occurring, right. So, one cannot simply put the threshold values randomly, there has to be some differentiating points in all the regimes. Okay. So, threshold selection could be one challenge. So, determining the appropriate threshold value which is given by gamma or the transition function parameters can be computationally intensive. Now, the second problem could be overfitting. So, let us say adding too many regimes can lead to overly complex models which generalize poorly. So, let us say if you have lots and lots of regimes, so let us say 10 regimes or 15 regimes or 20 regimes, that again might be a problem because that might lead to overfitting. So, adding too many regimes can lead to overly complex models which generalize poorly. And then thirdly, data sufficiency. So each regime requires sufficient data points for reliable estimation. So if you don't have sufficient data points inside each of the regimes, that might be a problem in itself. So again, these could be some brief challenges when it comes to, let's say, modeling using regime idea. So in the earlier slide, we talked about advantages, but then at the same time, I should understand that regime modeling is not free from any challenges. And then some of the challenges which exist are, let's say, threshold selection or overfitting or data sufficiency, etc. Okay, so now we pay attention to the very first kind of a model, which is called a threshold autoregressive model. So in itself, we have a very wide umbrella of different kinds of threshold models. And then the very first one that we'll discuss is called as TAR model in short, or the threshold autoregressive models. So firstly, just to give you a brief introduction as to what you mean by the TAR model. So in short, we can call them as TAR models, by the way. So threshold autoregressive or TAR models are a class of nonlinear time series models where the behavior of the system switches between different regimes depending on whether the threshold variable exceeds a predefined value. So I think even in the last session we gave a small introduction of threshold autoregressive models which make use of a threshold value as such. So let's say again, just to give you an example, let's say if you have a time series and a single threshold value like that, and let's say the time series is behaving something like this pre the threshold, and then once the time series crosses the threshold, you can see a lot of volatility in the time series. Okay, so a simple TAR model can be applied on this because it contains one threshold value and then you have transitioning from one of the thresholds to the other basically. Second point is this structure makes the TAR models well suited to capturing abrupt changes or regime shifts in the time series data. So I guess this entire slide is more from a basic point of view as to just give an intro about threshold autoregressive models in general, or a small motivation as to where can one apply the TAR models, under what situations can one apply the TAR models, etc. Now talking about some of the key features of TAR models, right. So the very first key feature is regime switching, obviously. So the model assumes different dynamics in separate regimes. We have discussed this point number of times so far, that each regime has some different dynamics when it comes to, let's say, different characteristics of the underlying time series. And the second important point is each regime could be modeled by its own AR process or by its own autoregressive process. Okay? So let's say if the overall time series is being divided into two regimes by deciding upon some threshold value, then on one hand I can put forward a certain AR model, let's say AR1, okay, and on the other hand of the threshold value I can put forward another AR model, let's say AR2. So how do you combine these piecewise AR models to form an overall kind of a TAR model is the idea here. Then the second ingredient or the second key feature of the TAR model is the threshold variable itself. So the threshold variable is such which determines the actual regime. Commonly this is a lagged value of the time series itself, let's say yt minus d. So yt minus d is some lagged value of yt itself, right. So let's say yt is a time series, so depending upon what value d takes, let's say 1, 2, 3, 4 whatever, so yt minus 1 or yt minus 2 or yt minus 3, any one of the lagged values could be taken as a threshold variable. Then the third idea is piecewise linearity. So although non-linear overall, the model is linear within each regime. Okay, so I think we discussed this point even in the last session, that if you delve deeper down into each of the individual states or individual regimes, then I can actually fit some linear models inside each of the regimes. And again, in front of you, even you can see the same thing in this example as well, that both the autoregressive models are sort of linear models, and I am trying to fit the individual AR models inside each of the different regimes. And lastly, flexibility. So handles processes where the relationship between variables changes depending on the state of the system. So these are, I think, some of the key features when it comes to TAR models or modeling using a threshold autoregressive kind of a structure. Now we will pay some attention into the model structure itself. So again, don't be bogged down by all the notations. So again, if you are not very comfortable by any of the coefficients, any of the notations here, again a suggestion would be to go back, let's say not just this week, but then maybe some of the elementary weeks as well, and then try to understand as to what the individual notations mean. But in general, since we are discussing a very easy sort of a model to start with, which is based on the autoregressive nature, it should not be very difficult to understand that where do you stop the model, right? For example, what do you mean by P? So again, even before discussing, I am very sure that most of you might remember what you mean by P. So if you are discussing any AR model structure, then you should be very comfortable by knowing as to what is the meaning of P, or for example, what do you mean by ET, etc. Okay. Alright, so what exactly is the model formulation? So the simplest threshold model where the autoregressive or AR process switches regimes based on some threshold. And then this is the model formulation in general. So yt equals phi 1 comma 0 plus phi 1 comma 1 yt minus 1 all the way up to phi 1 comma p yt minus p plus et. Now here the only difference is, rather than simply writing down phi 1, phi 2, phi 3 up to phi p, since we have two regimes or two states, I have to write down in this form. Alright, so the first row is true whenever yt minus d is less than or equal to some threshold value which is gamma. On the other hand, the second row is true, let us say phi 2 comma 0 plus phi 2 comma 1 yt minus 1 all the way up to phi 2 comma p yt minus p plus et, if this is true, which is yt minus d is bigger than gamma. And again, just a small description as to what the notations mean. So yt is a time series at time t, and then yt minus d is the threshold variable with lag d, and then gamma is the threshold value. And the most important point in this slide is this notation, which is phi ij, which is nothing but the AR coefficient for regime I. Okay. So phi I comma j, for example, phi 1 comma 1 would be nothing but the AR coefficient for regime 1. Similarly, phi 2 comma 1 is nothing but the AR coefficient for regime 2, etc. Okay. So again, you can pause the video, you can sort of ponder over this slide and try to understand all the individual notations as to what they mean. For example, phi 2 comma p or phi 1 comma p, etc. Now we will pay some attention as to what exactly the steps in model building. So the very first step is specify the threshold variable. So often a lagged value of the series. So often a lagged value of the series itself, let us say yt minus d, but it could also be some exogenous variable. So exogenous means some external variable. Okay. Now the second point is determining the lag structure. So you should always select the number of lags, let us say p in this case, in the AR process for each regime. And thirdly, estimate the threshold. So estimate gamma using techniques like grid search or minimizing the residual variance or using an information criteria, let us say AIC or BIC, etc. So these are some broad steps when it comes to model building. So specifying the threshold variable, then determining the lag structure, and then thirdly estimating the threshold value. All right. And the next step in model building is estimating the parameters. So once you estimate the threshold value, then inside the equations you have to sort of estimate or sort of find out all the parameters. So once the threshold is fixed, fit the AR processes for each regime using methods like least squares, etc. And lastly, obviously as always, diagnostic checking. So check for residual autocorrelation, stationarity and model adequacy, and conduct some hypothesis tests for non-linearity, let us say Hansen's test, etc. Okay. So these are broadly all the steps when it comes to model building using a regime sort of an approach. So estimating parameters, diagnostic checking, etc. Now towards the end we will describe what are the advantages of TAR models. So the first is interpretability, obviously. So the piecewise linear nature makes these models easier to understand compared to any other non-linear models. For example, let us say neural networks. Then the second one is flexibility. So the ability to model systems with regime shifts or asymmetric behaviors is one of the advantages of TAR models. And then thirdly, stationarity within regime. So each regime can be stationary even if the overall process is not stationary. Okay. And on the other hand, what are the challenges of TAR models? So the first one could be threshold estimation, as discussed even a short while back, that selecting the correct threshold value can be computationally intensive. Second is overfitting. So let us say adding too many regimes or lags can lead to overfitting. And thirdly, boundary issues. So sparse data near the threshold value gamma can make estimation very difficult. So firstly, what do you mean by the third point here? I will try to explain in a bit detail. So let us say if the overall structure has two regimes divided by one threshold value, and let us say you have a time series which behaves like that, And in some cases it might happen that just next to the threshold value you do not have any data. So, let us say if you have some missing data here and missing data there, and again let us say you have highly volatile kind of a structure here. So, this is called as sparse data. So, sparse data means that you do not have much observations near the threshold. This can make the boundary issue problem kind of predominant. So, boundary issue is exactly this problem, that sparse data near the threshold value can make estimation very difficult in a way. And lastly, a few applications. So, first could be in economics, let us say analyzing business cycles, expansion versus contraction, or modeling inflation dynamics with threshold like unemployment rates. Second one could be in climatology. So, let us say representing shifts in climate variables, for example, temperature, rainfall, etc., based on some external drivers. Or thirdly, engineering. So, let us say modeling systems with operational thresholds, such as let us say load bearing structures or machinery, etc. So, I think the second session in this week is more of an intro towards one particular kind of a threshold model called as TAR, or threshold autoregressive regime models. So, initially we started this session by describing in detail as to what are the different kinds of regimes. So, smooth transition regimes or Markov regimes or threshold based regimes, and then towards the end we discussed one particular time series example or one particular time series model which is widely applicable, which is called as a TAR or threshold autoregressive model. Thank you.